So in order to have continuous improvement, or Kaizen, right, that's continuous improvement that involves everyone, then we need to analyze the problem and develop a plan, and then we need to be able to test it. So we need to figure out some tools to help us analyze the quality within our company, and then some tools to help us come up with a solution or to figure out whether our solution is effective. So let's look now at some of the quality tools we can use to evaluate our company. So the first tool we want to look at is what is called a process flow diagram. So we created process flow diagrams early on in the semester. Remember, you have a starting point, and then you have activities or steps that are taken. If there is a decision involved, then it's a diamond. If you have to have input from someone else, so somebody else has to give you information, it's a parallelogram. If you need to get materials from somewhere else, it's a triangle. And we're showing the steps in our process. So a process flow diagram is important as a quality tool because if you remember, when we talked about where process was at risk, we used the process flow diagram. When we talked about the determinants of quality, we talked about product design, so what are we making? And then we talked about process design. Our quality can be at risk based on the steps we take to make it. And so it's very important that we have a process flow diagram so we can look at where our process might be at risk. And so we can create a process flow diagram with some critical control points to note where the quality is most at risk, and then in that process develop monitoring or ways to measure the quality at those points to make sure that we identify defects before they happen. So a process flow diagram is a very important quality tool. Other quality tools, the second one we're going to look at is what is called a check sheet. A check sheet has a diagram of your product and then a list of types of defects. And so what we're doing is we're looking at the different types of defects and where they occur. So you'll notice in this image here, we have circles that denote bubbles in our paint. So we have a company that's painting vehicles, and so here's the door, and here we have a bubble, and here we have a bubble in the paint. We can look at runs in the paint, scuffs in the paint, and you'll notice that we also have a tally for the number of each type of defect. So the check sheet is going to help us collect data about the type of defects and how pervasive they are. So where are these defects happening? Okay. And then we can start to look at how we can fix them. We can take information from our check sheets about the number of defects, and we can create a histogram. A histogram is a chart that shows frequency distributions. So let's suppose that you're a company like Amazon that has to constantly go and get orders from a warehouse. Okay, so you're filling packages. And this here shows how long it takes to retrieve the different items from the warehouse. So what we're looking at is that there's a number of times that we retrieve items from the warehouse, and they each take a different amount of time. So what we see here, for example, is that for 1 to 2 minutes, about 5 of our retrievals take 1 to 2 minutes. All right, 2 to 4 minutes, if we look at that, well, 2 to 3 minutes, that's 25 times we retrieved it. It took 2 to 3 minutes. And we can look for 3 to 4 minutes. There was almost 40 times, took 3 to 4 minutes. So by looking at a histogram, we can see what's the most common, in this case, retrieval time. If we were looking at the check sheets from the previous slide, we could make a histogram that would show us the number. Let's say that one door has 15 defects, another door has 30 defects. we could start to see what the most common number of defects per door was. So we're looking at frequencies, the number of occurrences of defects, and in this case, retrieval times. So the first thing we look at is, are there any extremes? So notice in our retrieval times, all the retrieval times are between 1 and 12 minutes. So the question to ask then is that acceptable? What is an acceptable amount of retrieval time? If an acceptable amount of retrieval time is between 1 and 10 minutes, then we can start to see how many times we went to the warehouse and it took more than 10 minutes. So really, our quality tools are supposed to lead us to questions. They're supposed to trigger for us questions about what's happening. So in this case, the question is, what retrieval time is acceptable, and do we have any retrievals that are outside of that? Okay, so what's our range of values? Are they in extremes? Perhaps this graph actually looks like this. So that's your 1 to 12, and then there was this one retrieval that took 30 minutes. So this is a flag, right? It's an extreme, an outlier, and so then the question is, well, why did that one time, why did it take so much longer? So what was it about that event that was different from the rest of these? So maybe we sent 2 workers to the back to go retrieve items for a shipment, and they couldn't find it. Or maybe they accidentally knocked down a bunch of other stuff, and then they were stuck putting that back together and fixing that, and that's why it took 30 minutes. So this starts to lead to questions that we can address and that will improve quality. We can also look at whether our distribution is symmetric. Notice in this case, we have a bimodal distribution. Bimodal, meaning 2 modes, 2 most common numbers. So what this tells us is that we have this group that essentially has retrieval times between 1 and 5 minutes, and then we have this other group that has retrievals between 6 and 12 minutes. So the question is, what's the difference between those 2 groups? This leads to questions, right? Who are these different groups? Well, maybe when we dig deeper, we find that the morning crew, when they go to retrieve items from the warehouse, it only takes 1 to 5 minutes. The afternoon crew, it takes them 5 to 12 minutes. So what's the difference between the morning crew and the afternoon crew? Maybe the afternoon crew is a little bit more sluggish after lunch, or maybe there's different types of orders coming in the afternoon versus the morning. So really, we want to look at these quality tools to help us ask questions, dig deeper, so that we can improve our quality. All right, so we talked about process flow diagrams, we talked about check sheets, we talked about histograms. For more information about how to create a histogram, please see the next video. All right, quality tool number 4 is what is called a Pareto chart. A Pareto chart is based on the Pareto phenomenon. So there was an economist named Vilfredo Pareto, and he was in Milan, Italy. And what Vilfredo Pareto found was that 80% of the wealth in Milan was owned by 20% of the households. And so the Pareto phenomenon, or this 80-20 rule, has expanded to be used in business. And so what we say is that 80% of our sales come from 20% of our customers. 80% of our problems come from 20% of our production. So the idea with the Pareto phenomenon is, rather than focus on every problem we have, let's focus our attention to those that have the biggest impact. Okay? So if 80% of our problems are caused by 20%, then we should focus on that 20%. So let's look at this example here. Okay, so this is a chart. It's organized from highest to lowest frequency, and in this case, we're looking at deliveries of pizzas. So what you see in the vertical columns here is the number of complaints about our pizza delivery company. So you'll notice that delayed delivery had 1,200 complaints, and pizza not being hot had 600 complaints. Now we have lots of different types of complaints that only had a handful of them. Damage, wrong size, less seasonings, incorrect billing, and so on. Rather than try to address all of these quality issues that only impacted a small number of people, let's focus on the quality issues that impacted the most number of customers. So notice here this line chart that you see overlaid on top of the column chart. Well, this little dot here shows you that if you can deal with the delayed deliveries, 1,200 complaints would have gone away. And that is, if we go across, that's what, about 50% of the overall complaints. So if you deal with just that one issue, 50% of your problems will have gone away. If we add to that the pizza not being hot, so we add the 600 complaints about pizza not being hot, the two combined, delayed delivery and pizza not being hot, is 80% of the complaints. So if we focus on just fixing those two things, delayed delivery and pizza not being hot, we will have dealt with 80% of the problems that our business has. So we're going to focus our attention on delayed delivery and pizza not being hot. To create a Pareto chart, you need to identify the different problems, different quality issues. You need to sort them so that the most frequency, the most occurring, is on the left, lowest on the right. And then you're going to overlay a cumulative chart, cumulative line graph, to show that as you add additional issues, what that does to the total. So check out a video after this for how to create a Pareto chart in Excel. All right, so we had process flow diagram, check sheet, histogram, Pareto chart. Now let's look at a scatter diagram. So a scatter diagram shows the relationship between two variables. So for example, on the right here we have temperature and we have the reliability of our product. Notice that as the temperature gets hotter, the reliability of our product declines. So we can start to better understand what's impacting the quality of our product, what's hurting the quality of our product, by looking at related variables. So in this case, temperature seems to be related to the reliability of our product. The hotter it is when we produce the product, the less reliable the product is. So when you look at a scatter diagram, you plot a scatter plot with your points, and then you do a line of best fit. And we're looking at the level of correlation, and we're looking at R squared. What do we call R squared? R squared was the coefficient of determination. It told you the percent of variation in your one variable, so the percentage of the change in temperature that explained the change in the reliability. So we can look for the R squared, and if you have a high R squared, we're looking really for 0.8 or higher, then you can use that variable to predict your other variable. So then we can start to say, okay, well, look at how temperature is related to reliability, what's happening with the temperature in our production, and what could we do to keep the temperature lower so that we don't have these issues. Or let's ask ourselves, what's wrong with the process design or the product design that makes it so susceptible to a temperature change? So either you can use the variable to help you control your quality, or to understand what's impacting it and then make future changes. The sixth quality tool is what is called a control chart. So in a control chart, we have some kind of target that we're trying to achieve, and then we're looking at the amount of variation that's allowable. So it's going to be a line plot of time-ordered values. So notice there's time on the horizontal axes. and we're going to have some kind of sample statistic that we're measuring. And we're going to have control limits. So again, we have a target, and then we have how much variation from that target are we going to allow. So you're going to have an upper control limit and a lower control limit, and you're going to look at how far off you are. So how do we set this up? Well, when you set up a control chart, it's based on the empirical rule. So recall the empirical rule from stats, and the empirical rule says 1 standard deviation, plus or minus 1 standard deviation, is 68% of your data. 2 standard deviations is 95%, and plus or minus 3 standard deviations is 99%. Right? So if this is our average, 1 standard deviation is 68%, 2 standard deviations 95%, and 3 standard deviations is 99%. So when you set your upper and lower control limits, how much variability will you allow? Do you want it to be 1 standard deviation, 2 standard deviations, and so on? So if you think about this as your standard normal distribution here, the upper control limit and the lower control limit are going to be set by that empirical rule. How much variation will you allow? So let's suppose that we're going to include 99.7% of the data. So our upper control limit will be our average plus 3 standard deviations, and our lower control limit is the average minus 3 standard deviations. Okay, here we have our average in the middle. Okay, so when we look at our control chart, there are some things we want to look for. Do we have any points outside the upper and lower control limits? Extremes, anomalies, outliers. Is anything fall out here? And if you find something that falls outside of your upper or lower control limit, then that needs to beg the question, why? What happened? What's going on there? So you need further investigation. So we're going to look for a couple things. We're going to look, is there anything outside your upper control limit, lower control limit? Okay. The other thing we're looking for is there a pattern in your data? So in this table we're looking at here, we're filling bottles of ketchup, and we have a target for how much ketchup we put in each bottle. There's an upper and a lower control limit, so there's some variability we will allow when we fill these ketchup bottles, but we don't want to overfill a ketchup bottle, which is that point above the upper control limit. We also want to identify if we are consistently over time under or overfilling the ketchup bottles. So notice there's a period of time in which we are consistently underfilling the bottles. So do we have multiple points on one side of your target? Okay. That's telling you that for that period of time, so this is what, 8 a.m. to 1 p.m., we underfilled all the bottles of ketchup during that time. And so the question is why? Was that a different shift of workers? So do we have an issue with the attentiveness of our employees? Had we just recently done some maintenance on the equipment and they were underfilling? So again, it's triggering questions about what's going on for that period of time. The other thing we need to look at is, do we have consecutive points outside of 1 standard deviation? So if your upper and lower control limits are based on 3 standard deviations, okay, we can find the point at which we're at 1 standard deviation and look for, do we have consecutive points like these that are outside of our 1 standard deviation? So why did we have multiple points in a row where we were underfilling? Really what should happen is it should be random, right? we're filling ketchup bottles, and some of the time we're going to overfill it a little, and sometimes we're going to underfill it a little, and it should be random. There shouldn't be a pattern to it. With the control chart, we're looking for, is there a pattern? Do we have consecutive points that are on one side of your target? Do you have consecutive points where you have, like in a row, you're outside of one standard deviation? And then do you have any extremes that are outside of your multiple standard deviations? So we're looking for anomalies, flags, that get us to ask questions about what's happening with our production. If you wanted to learn how to make a control chart, please see the following video. All right, so we had process flow diagram, we had our check sheet, we had our histogram, we had our Pareto chart, our scatter diagram, our control chart. Okay, we have two more that we want to look at. Number 7 is what is called a cause and effect diagram. It's created by a guy named Ishikawa, so it's also called an Ishikawa diagram or a fishbone diagram. The way that a cause and effect or Ishikawa or fishbone diagram works is we have some kind of issue, okay, some quality issue. In this case, we have metallic substances that are appearing in the product. Okay, so we have some metal flakes. And then the cause and effect diagram helps us to understand why that might be occurring. So this is a diagram used to organize the causes of a problem. And when we are looking at the possible causes of a problem, we have 6 M's that we should focus on. Is our problem caused by measurement? Okay, so if we're looking at metallic substances in the product, is it simply that what we are using to measure the amount of metallic substance in the product, is there a measurement error? Is the sensor not working? And so it thinks there's metallic substances there when they're not. Maybe it is a machine issue. Maybe the materials we're using in our production or the machine that's doing the assembly has a broken piece on it. And so it's adding metallic flakes to our product, and it's coming off the machine, or it's coming from some of the pieces of the machine. Could also be coming from some of the materials we're using. So if the pieces that are being assembled are made of metal, maybe some of that is flaking off. So it could be the materials, it could be the machine, it could be they're not a problem at all, it's just in our measurement we're recording a problem when there's not one. Maybe it's related to manpower. So is there something that our workers are doing that could be causing the metallic substance? So is it the tools, the equipment they're using that's breaking? Is it poor or improper training that's leading to this? Okay, so to look at our workers, we have to look at our methods. So we look at our process design. How are we making this product? Okay. Is that causing it? Is it the methods that we're using? And then lastly, we have Mother Nature. Okay. So is there something else unpredicted, out of our control, that could be causing the metallic substance? So as we look at possible causes of any particular quality issue, we should be able to come up with some possible causes that are measurement related, machine related, materials related, manpower related, related to our methods, and related to Mother Nature. That is outside of our control. All right, the last quality tool we want to look at is what is called a run chart. And a run chart, just like the control chart, looks at what is happening over time. So it's a line plot used to track the values of a variable over time. So here we have an example of a hospital, and these are falls that are happening in the hospital. We would expect, it to be random, right? That when people fall down in the hospital, it just is a random occurrence. If we see a trend, then there's a quality issue we need to address. So for example, what if there are more falls on weekends? What does that tell you? Well, what's the difference between the weekends at the hospital and the weekdays? Maybe there's less people on staff on the weekends, and so we have patients then who are getting inpatient, waiting for a nurse to come see them, so we have more of our patients getting out of bed when they shouldn't, and so they're more likely to fall. So what we're doing is we're trying to identify issues by looking at our data. So our tools help us identify issues and ask the questions. And then if we come up with a plan to improve quality and we implement it, even on a pilot process, so even if it's just, the do in the plan, do, study, act, then we should see a change in that in our tools and our analysis. So we had a total of 8 quality tools, process flow diagram. We have the check sheets to help us collect the data. We have histograms, Pareto charts, scatter diagrams, control charts, cause and effect diagrams, and run charts.